Pieter is the sole Goldman Professor of Astronomy here at Yale. He's won many prizes, most recently the Yale Graduate Mentor Award in the Natural Sciences. He's won the Mark Aronson Memorial Prize and has done a variety of named lectures, including at Caltech and Cambridge. He has revolutionized the study of diffuse galaxies, enabling a lot of fun new studies of dark matter. We have not asked him here today to talk about any of that, unfortunately, or fortunate, I don't know, anyway, one way or the other. We've asked him here for his role on the Astrophysics Decadal 2020 Steering Committee. The astronomy, as Pieter will no doubt tell us, the astronomy community comes together every 10 years or so and decides what the most pressing scientific questions are for the next 10 years. This, in turn, dictates much NSF funding in that decade. So it's something a lot of people pay a lot of attention to. So we're very happy to have Pieter here to tell us all about what the astrophysics community decided were the most pressing science questions over the next 10 years. Thanks.
Yeah, thanks. It's good to be here, and I'm very happy to come back all the way from Hill House to talk about science as well. Anyway, I will talk about science, but in a very big scale. Yeah. So as Laura said, this is a once every decade, roughly, exercise. And it's really great because it means that the astronomy community, writ large, speaks with one voice in a sense, and it makes it easier for agencies to advocate, in Congress and other places for these priorities, because there's no, usually there's no dissent among the astronomers or among the community. And everybody comes together and comes with these ideas, and it's been quite successful. It's led to the Hubble Space Telescope and many of the big projects that you may know about in astronomy over the past 30-40 years. And so yeah, we did this over the pandemic, which wasn't too great, but it took about 2.5 years and about 100 meetings, mostly on Zoom. Which was really hard, but we managed to get some kind of approach going to do that. And our brief was to be ambitious, which sounds kind of logical or even like a throwaway thing, but we were ensured that it was not. That both NSF and NASA we're looking for something quite major, sort of a vision for the next decade, or as we'll see, even beyond, that was not sort of holding back. At the same time, they gave us funding profiles, of course, and but we were encouraged to follow the optimistic funding profile that was provided to us. So it was different from the last decadal survey, where the brief was more like, don't ask for too much, because funding will be tight. Now we'll see, right? NASA and NSF don't operate in a vacuum, and so a lot depends on Congress and what happens after. But that was the sort of pleasant aspect of the whole thing. At least we could think big and think broadly. That was we were encouraged to do that. Yeah, and like I said, it was mostly over Zoom. So this is the steering committee, and the way this process worked was it's a bottom-up process in some ways, where it started with white papers that were solicited from the community. So there were about 1,000, and then those fed into both science panels that discussed, what are the major questions over the next decade and beyond, and program panels, which discuss facilities, like what are the proposed big things that can be built, and what should we prioritize. And then for the first time, we had a panel on the health of the profession, societal impact, and the state of the profession, which was really great. They looked at things like demographics and diversity, and also funding. How can we fund individual investigators, that kind of thing. And so for the first time, there was a specific panel at the same level as the program panels and the science panels to address that. And then that all fed into the steering committee, and steering committee members were also embedded in the program SOPSI and science panels. But then after that, it was our job to kind of synthesize everything and come up with a report. Yeah, so this is a lot of words, which I will not make you read. The way the report is structured is it starts with science questions, and so that's the top there. And we identified these 3 major science areas, and then within each of these areas, a specific topic that seems ripe for exploration, over the next decade. So that's that top thing. So these 3 areas, which I'll go over. And then there's the foundations at the bottom, which has a lot to do with like, how do we actually manage the day-to-day life, you could almost say, plus things like, laboratory measurements and, making sure that the pipeline for instrumentation remains intact, those kinds of things. And then the big middle thing is essentially the actual plans, both ground-based, largely NSF, and space-based, largely NASA. And yeah, so this is recorded, so later you can look at all these things, and I can also provide the slides. Anyway, we'll start at the top. So there's these three major themes. The first is not a surprise probably to anyone. That's about worlds and suns in context. And so the idea is that by now it's no longer about discovering planetary systems, but understanding them, and looking at atmospheres, looking at habitability, but also looking at the demographics of planets, which turn out to be vastly more complex than anyone expected. And so this field has almost taken on a life of its own. It's split off, conceivably split off from astronomy at some point in some sense, because it's a major undertaking of its own. But anyway, so that is the first major theme, and the roots there are fairly clear. There's the life route, which is essentially trying to first identify habitable planets in terms of their temperature and things like that, then to study the atmospheres and then look for biomarkers. That's that particular train is in motion, but it may take 30 or 40 years, to get where you want to go there. Well, not literally, but but there's a lot of other things, like this ALMA image here of a young planet-forming star. It turns out that you can see solar systems, being created as we speak. In the infrared, the dust lights up, and you have these dark rings, which is the location of a planet in this protoplanetary disk. And so you can do amazing studies that people didn't really think about, before these facilities were built that are producing these data. But then, yeah, so this is kind of what I said, that it's pathways to habitable worlds, the priority area. So that's the specific thing within that large field that is sort of ripe for advances. What do you need for that? Well, big telescopes, largely. The size of the mirror helps you collect photons, but it also creates, it allows you to image these things with great resolution and contrast. So you need to isolate the light of a very little planet next to this bright star, and which is incredibly hard. And but people are very smart, and they have developed techniques to do that, but they require large apertures and to get a lot of photons, to get high resolution, and incredibly high quality optics and things like that. And so the two big things that will help with this is very large telescopes on the ground. So ELTs are extremely large telescopes. very imaginative. Those are like 20 or 30 meter class telescopes on the ground. The largest telescope we have now is 10 meters, so that's a factor of 3 or so larger in diameter. But the high contrast imaging goes as d to the 4th, so you have a huge gain of hundreds when you build a telescope that large. And then a space telescope, because that's what you ultimately need for the stability, to be outside of our atmosphere. So here the idea is to develop a very large telescope in space, a successor to Hubble in terms of wavelengths, ultraviolet and optical, largely, but vastly more precise in terms of its figure, and also off-axis, so that the light bounces against the mirror, but then doesn't bounce back, and you have no obstruction in the light path that's really needed for this high contrast stuff. So that's that. Then the second science theme is the revolution in gravitational wave detections, and also IceCube with the high energy neutrinos, and CMB. There's been incredible progress the last decade in all these areas, and we can build on that. Here, most of the facilities are already in development, and that's actually sort of a mismatch between this slide deck, which is the one I'm supposed to present as the Decadal survey slide deck, and what's relevant over the next few years, because some things were already approved a decade ago and are coming online in the next few years. So I snuck some of those things in because that's in a sense more relevant to you than the things that happen in 10, 20 years. So anyway, so in gravitational waves, this is a very important theme in terms of science, and here, there's these new windows on the dynamic universe. That a lot of these things are time dependent. There's something that goes off in the universe, huge burst of gamma rays or emerging black holes, those kinds of things. And the idea is to study those transient sources as they appear in the sky. As I'll discuss, we already have some of the means to do that coming up in telescopes, such as the Rubin Observatory, which is going to come online in just a few years. Another science theme is then cosmic ecosystem. So here, the realization is that cosmology and galaxy formation are linked. It's become clear that a lot of the processes that are key to understanding how galaxies were formed and how they evolve happen on very large scales. They have to do with how gas flows into galaxies from the cosmic web, and then how outflows from those galaxies interact again with that gas. The gas traces the dark matter is the idea. Trying to understand these filaments of dark matter that connect the entire cosmos, and then the gas that flows within those to galaxies and out from galaxies, that has emerged as being key to understanding how fast galaxies form stars. Even their central engine, the active nucleus in the middle that comes from a supermassive black hole, is fed by that gas, and it also provides feedback through jets to that gas. And so this whole ecosystem of star formation, gas accretion, and outflows is outside of galaxies and inside galaxies is going to be a major theme. Right now, that gas is just essentially impossible to detect. It's very, very faint because it's very low density. But there's a lot of facilities coming online and proposed here, and that can do that. So that's an important theme. Then the specific goal is to see, what causes a galaxy to grow. Very fundamental question. We've mapped how they grow largely now. Over the past few decades, we know, okay, a galaxy like the Milky Way had about 1% of its mass 10 billion years ago. It then grew slowly, largely, by increasing the number of stars, not much size growth. And then, we know roughly when the disk of the Milky Way formed, when the bulge formed. So we have a pretty good map of galaxy formation now. Now the question is why, right? What processes drove that evolution. And so you need, what do you need? You need to identify what those drivers are. And so for that, as so often the case in astronomy, you need a wide range of wavelengths. And in particular, you need to understand how black holes interact with galaxies, because that is a major theme. We think that they drive a lot of the star formation in the galaxy, whether they form new stars or not. And we also need to be able to peer inside dust. That's also something that we've learned the hard way, that unless you know how to deal with obscuring dust, it's very difficult to make out what happens inside a galaxy. So that requires infrared observations where the dust is re-radiated, the ultraviolet radiation is re-radiated by the dust. And so you end up with optical information to particularly to identify where the gas is through absorption lines, X-rays to identify these active nuclei, and X-ray gas, diffuse gas, and then infrared to identify the dust and look inside. So those are the big themes, and there's a ton of detail in the report and various places in the web. Every one of those themes has its own report, believe it or not. So there's a ton of detail that went into all of this. So, you know, I feel I can't do any of it really justice. Then there's the foundations. So there's maybe somewhat less interest to this room in terms of, like, you know, the nitty-gritty of how things work. Then again, you know, it is super important. So I would like to talk a little bit about it. So again, we had this, the first time we had this panel on the state of the profession, and it was really great. They have they have their own report, which is really an excellent read to sort of using metrics and using objective criteria, lays out, you know, what the issues are, and also proposes solutions in the sort of the day-to-day of what we do. You know, one of the things in terms of equity is demographic data. Sounds very boring and a bit of a cop-out, but it's not. It turns out NSF, for instance, is extremely reluctant in providing, you know, people in the room here know way more about this than I do, but we ran into this on the panel. To just get basic demographic data is almost impossible. The agencies are extremely reluctant to provide sort of the first step information that you need to even describe the problem, if there is a problem, right? But you start to think there is a big problem that you don't even get access to the data. Anyway, so there's recommendations that follow from the little bit of data that we do have, you know, one of the key things is the pipeline, of course, and bridge programs to make sure that people are that we invest in people not just after they arrive, but also before they arrive, and through the whole process of becoming a successful astronomer. Again, that's not limited to like building big things. This is really crucial. If we can't fix these things, then, you know, sort of what's the point? Dark skies, that seems an odd topic here, but we had to put it somewhere. That has to do with Starlink, you know, and all the things shining down on us. I'm happy to talk about that if somebody asks. This is more of the sort of the basics, lab measurements again, theoretical underpinnings. The problem here is that there's often not a lot of funding for these things, and also, frankly, not a lot of appreciation in the community. And so we tried to give it a more prominent place in the report. Now, I should say that a lot of previous reports tried to do the same thing, and same with grant funding, which I'll get to. So whether anything actually happens is beyond what we can influence. This was a big one, the NSF grants. So the success rate for the general astrophysics grants have dipped below 20%, and that gets to be not sustainable for people, because this is what, you know, people use to pay everything, right? It's not just to support students and postdocs, but also page charges, travel to conferences at many places, Yale to some extent too. You don't have any other source. If you don't get your sort of this rolling grant from NSF on some program, you're out in the cold. Success rate for first-time applicants, 7%. Okay. Also, and this is not, again, we couldn't get the data, but in the medical science, there's a huge gender imbalance in second-time applicants. Men send in the same proposal next year. Women think, okay, apparently it's not good enough. There is also a lot of hidden, and so if the success rate first time is 7%, you know, you're in real problematic territory when it comes to these things. Again, we couldn't investigate it because the data wasn't available. But in other fields, there are very unfortunate side effects of such a low first-time acceptance rate. Anyway, yeah, that's, and also first time, somebody who applies for the first time means that they're just starting out, right? This is the moment when they need the funding the most and can make a mark. After running the gauntlet and you're finally a faculty member, you know, you're less than 1 in 10 chance to actually fund your program, which is not great. So yeah, we, as previous decadals, we said it should increase. We were very specific. We were told, like, you know, don't say double it because it's not going to happen. You know, and as I'll discuss, there's another problem in the NSF budget that needs to be fixed. So we had a very specific recommendation based on, you know, a goal success rate of 30%, which we see as sustainable. In other sciences, by the way, I don't know if I have the graph in here. No, in physics in particular, it's higher. You know, it's about 35%. Now, that's the data that we were given. So it is low compared to most other fields. Okay. Anyway, so that's the foundations. Then what are we actually proposing? Now, this slide is it's just one slide, but I'll come back to it at the end. This is the stuff that we didn't talk about because it's already happening. And so for us, it was not relevant, except that we were asked to comment on these things. And so we did, you know, we had like little reports on all of these topics. But these are happening, like the Vera Rubin Observatory, which is a giant 8-meter telescope that's being built in Chile to survey the entire sky every 3 days. So it's completely revolutionary in terms of transient phenomena, supernovae, all of that. Also, it will create ultra deep images of the sky over time. So any place in the sky, at least visible from Chile, you'll have a beautiful, deep multicolor image in the future, you know, which is completely new. That'll start operating in 2024. So, you know, that's like right around the corner. And a major goal is dark energy and other things. But transients and dark energy are the big drivers. And asteroids. Yeah, that's politically very good and interesting. So yeah, in space, then the big things are the James Webb Space Telescope, JWST, which I'll talk about at the end. Roman is a successor to Hubble, basically, but very wide field. So it'll take huge areas of the sky very quickly. Not bigger than Hubble, a little smaller, but so we'll have high resolution imaging over a large fraction of the sky also in the future for weak lensing and all those kinds of things, very important. And then Athena and Lisa I'll also mention. So anyway, so we recommend, yeah, do all these things. That's what we said. We did not, we did not, I didn't put that slide in. We did not recommend continuing SOFIA. That was another thing that we were asked to comment on. That's the Boeing with the telescope inside. Very cool, very expensive. And so we advised to terminate that at this point. Yeah, so then what did we recommend for the future? You know, there's two things. One is large strategic missions, and this is for space first. large strategic missions. And then second is the sustaining programs, which is essentially to make sure that we have something to do while we're waiting for these big missions. That's one translation of that. The idea is that rather than recommend one mission or two, we recommend a mission and technology maturation program. And so that is because these things have gotten so big that they take many decades to complete, and so risky for the entire astronomy operation that they have to be reviewed before you really pull the trigger. And and that means yeah. So let me get to that. The order is a little weird, but that means if you do that you spend a lot of money, and as we'll see in 2 slides, almost $1 billion on the first one, the infrared optical UV mission, before you even decide whether you want to do it or not. And so it's a scale that we haven't really touched on before. So this review is kind of critical. So between those 3 things, the infrared optical UV, high resolution X-ray, and the far infrared imaging and spectroscopy, those were the big sort of 3 fields that we were considering. The priority is for the infrared optical UV, and there the planets sort of lead the way. This idea of developing a 6-meter telescope in space in optical UV that is beyond anything that's exists or could exist in other countries or in other means. It's something that you can sort of do, it'll be completely transformative for like 50 years. It's the kind of thing that is a huge leap and a huge change in what we can do, but also a huge risk. And particularly the big risk was JWST, which launched right after our report was done. And so we're like, if that blows up on the launch pad, then, big X through all of these. But it's the opposite, which we'll see. It's been a smashing success. So that's a huge boost to building an even more capable one in the future. Anyway, so the idea is to start with that, do a lot of research on how to do it, and then also do research on an X-ray mission and an infrared mission, and then have a phased approach of implementation. Sustaining programs, so that's a time domain and probe missions. So there the idea is that there already are Explorer missions, which are up to $300 million, to develop, and they're very successful. A whole bunch have been done, and they're great. But then there's these big projects, as we'll see, they're 10 billion plus, and then there's suddenly nothing in the middle. And so these probes would be up to 1.5 billion, not peanuts by any means, and there would be sort of one a decade is the idea. Because building these big things is decades, multiple decades. All right, so yeah, this is kind of obvious. This is the funding issue or context here. Yeah, so we have Hubble, which turned out to cost about 9 billion, not when it was proposed, mind you. And Compton Gamma Ray Observatory, which is cheap by comparison, 1 billion, Chandra 3 billion, and JWST 11 billion. Okay, huge cost overruns, was never the intent, but that's what happened. Roman 3.5 billion. But now we look at these proposed missions. These are the big 4 that we had to analyze. LUVOIR B was their small one of the LUVOIR team. We didn't even look at LUVOIR A, frankly, because that's a 40-year, 50-year project, with a price tag of like 30 billion. And so these are the costs: 17, 10.5, 9, and 10.6. So for our highest priority thing, it's 17 years and about 20 years development time. Everything optimal, right? That's with optimal year. The assessment is done for the immediate start and optimal budget profile. So when everything that you need to buy is available right when you need it. which is great, but not always.
Can I just interrupt?
Yeah, sorry, I'm a bit slow.
Top table, the numbers are what was spent.
Yeah.
Bottom table is the predicted number.
Yeah. Oh no, come on. We now it's all perfect. Now, true, but yeah, these are not the costs that the projects gave us, though. These are so there's this company, Aerospace.
Aerospace did estimates on, you know.
Yeah, no, they didn't actually. That's since then the last decade they did, but that was the first time. So an outside company is hired who have experience with big projects, and they are asked to independently assess the cost of these missions and also the risk, cost and risk. And so they can talk to the projects, but they are not beholden to the projects. So that's how all these cost estimates are done now. Leading, you know, like I think Louvois was 10 billion according to the project. So, you know, a billion here, a billion there. Or, you know, it's real money, yeah. Anyway, okay, yeah, lots of money, lots of time. So that's why we came, so again, the order is a little weird, but that's why we came to this idea of this maturation program. You know, this huge cost and time. So we're talking multiple decades. And so what can we do? We also don't want to tie the hands of future decadals too much, right? That there's no decision to be made 10 years from now. The highest priority then is for this this optical thing. And again, 800 million is required before the review, before we can transition to actually adopting the mission. That includes building prototypes and all that, you know, technology demonstrations and things. It's not just sketching, you know, in a corner. And then co-equal priority, we didn't want to, you know, again, over-constrain the future, is an infrared and an X-ray telescope. Now, the important thing is we're recommending all three, but in this phased approach. People expected us to pick one and then say we're not doing the others. But here the idea is that actually there's some funding for these other projects right away, ramping up as time goes on, and particularly after a review, like 5 years from now. 6 years from now. That's the idea is that you know, all these projects are then phased and they're in their own little timeline. That also works way better for the budgets. Okay, so that's the optical telescope. I have to speed up a little bit. Yeah, the idea is the main driver for the optical telescope is habitable worlds, and so we'll find you know, about 20 Earths with, like, you know, where you can detect oxygen and things like that is the idea, based on very unknown estimates, of course, but thousands and thousands of other planets, of course, slightly more massive than Earth. It's partly, yeah, just because it's Earth, we are extra interested, but a planet that's twice as massive as Earth and is also quite interesting, of course, if it has aliens, say. Okay, time domain is a big feature. There's so many areas now of astronomy that are key to the time domain, so this is a recommendation that there's actually a time domain program to coordinate and to be able to follow up multi-messenger events. So if something is detected in gravitational waves, but you also want to have the electromagnetic signature at as many wavelengths as possible, how is that done, you know, in sort of a coordinated way? There could be an Explorer scale mission, for instance, to help do that. So this is what I explained, that the probe line, which sits in between these giant missions and the small ones. And again, X-rays and infrared are now in our timeline are 25 or 30 years away. So are we not going to do any X-rays or infrared beyond what we have now? Seems a bad idea. So it is a possibility, but this is competed. It's going to be competed that that we have a probe mission, you know, to sort of fill the gap and be able to do unique things, targeted things, not a general purpose mission maybe, but for instance, a specific targeted X-ray probe or infrared probe in the meantime. Okay. Yeah, this is the SOFIA recommendation, the program of record. That's everything that's going on right now. Athena has its own, that's the European X-ray mission. We thought when we were doing the report, like, X-rays are fine. They have Athena. It's all going to be good. Big European mission with NASA contribution. We don't need to do anything in X-rays. And then right after the report was done, there was a review and cost review, and it's going to be descoped. They had a cost overrun 1.9 billion out of the 1.1 that they had. Which is too much, and so it's going to be probably going to be descoped, not canceled, I hope. Anyway, this is the kind of thing that happens that we didn't anticipate. So then for the ground-based large programs. So here the big thing that we recommend is investment in these big telescopes. So at Yale, as some of you may know, we've been talking for many years about being partners in a large American project to build the next generation large ground-based telescope, 20-30 meters. We're now part of Keck, which is the biggest telescope in existence now. So Mauna Kea, not the volcano that's exploding, the other one on the Big Islands. And there's plans to build 2 other big telescopes, 20-30 meter in size, again, a lot bigger. But we haven't done so. And what's happening now is it looks like, at least that's what we're proposing, there'll be an NSF contribution to these telescopes. They kind of need it to finish. So in a sense, it smells a bit like a bailout. You can also see it as a huge opportunity for the US to come in, and actually for the federal agencies to come in and actually secure time for everyone in the US, not just the people who started these projects. And so that's the big recommendation from the ground. Now here's the thing I alluded to earlier, the NSF budget for astronomy. And the issue is what is shown here in the graph is the fraction of the total budget that goes to operations of facilities. Okay, and so green is astronomy, blue is physics, and then there's other things. And so it's high and it's going up from 60 to 80%. So what happens is you get funding from NSF to build this giant instrument, but then they want the operation costs to come out of the general astronomy budget. And it's not working. It's too expensive. So we've been too successful in building large things, you could argue. But we've now said, like, either this is fixed or we can't do anything big like the ELTs. It just doesn't fit. Then 100% of the budget would go to operations, and there would be 0 money for grants, for instance. Right? That comes out of directly the same money. This rise, by the way, is due to ALMA in Chile. Again, a new facility, wonderful. But 80% is not sustainable. So the ELTs, I'll kind of skip over that. If you have questions, then please ask me. We're also recommending CMB experiments. This is a small contribution from NSF. It's largely DOE and physics. It's actually the next generation CMB instrument will provide so many possibilities that it's also interesting to sort of general astronomers and not just physics, which is a point that they often make, but I think it's now true. They'll look at the whole sky every few days, et cetera, et cetera. And, okay, it starts to sound almost plausible. Anyway, so yeah, that's CMB. There's people in the room who know more about this than I do. Next generation VLA, big radio telescope. We essentially said no, but we said no to the immediate question, which was to spend $3.2 billion on it. We're like, I know, but here the ask is actually almost twice as large as for the ELTs, and that's because there's no NSF would be the major funding source. But we said it's good to do a review and a project scope and design exercise. Basically, between the lines, it's like make it a lot cheaper and then come back. But meanwhile, there's money to do the research to see how to make it cheaper and how to make it smaller and still be competitive. Mid-scale, I'll skip that. Important, but there's not much specifics to say. but ask me if you want. Gravitational waves. So I have only one slide on it, even though it's a huge topic. But that's because we're committed to doing LISA, or at least that's the plan. And so there is a big mission, that's planned in space, mid-2030s. So a little while from now. And so there's also ground-based plans. Cosmic Explorer would sort of take LIGO, but make it so sensitive that it would detect millions of events. Every little wiggle in space-time would be detected, turning it into a real observatory rather than a, event detector, a fundamental change. And so we're saying, yeah, by all means, go ahead and develop technology for that, but there's no immediate ask at this point. Ice Cube, same, we're happy, keep going. That was sort of the physics. Physics asked us to comment on some of these things, and even though the contribution from NSF was small, just to see if we supported it, and definitely here. All right, so we'll skip that. So this is the last slide in the deck, which basically shows the timeline for all these things. Now, again, as I said before, there's a gap between 2022 and 2030, right? It's like everything starts in the mid-2030s, which is a problem for these decadals. They now spend so much time that it doesn't quite work almost. So that's partly why we did this phased approach, that there's decision moments and gates that future decadals can pull the plug or change priorities. But anyway, I just wanted to highlight there is stuff coming that I only touched on, right? We just had JWST. Then Rubin, I talked about, this is this ground-based telescope that will image the entire sky every 3 days. Then there's Roman coming after, which is this space telescope like Hubble, but wide field for lensing and other things that will compete with Euclid, which is going to be a few years earlier, European version. But where NASA has a contribution to Euclid as well. And then even further along, LISA, hopefully mid-2030s. Athena was 2035. We'll see if the review speeds it up by descoping, or it gets delayed because they ran out of money. It's hard to predict right now, but it'll be a while from now. But it's coming, and it's not on the graph. So it's like, I felt I needed to at least highlight that. Now, I just want to end with JWST, because that just came online this summer. The first data were released in July. And so it made the cover of Time, or at least Photos of the Year of Time, not Person of the Year. Thank God. It was web. It wouldn't be good. Anyway, yeah, this is the picture. What the telescope did, which is very different from Hubble, was the very first data it released was a very deep image of sort of an interesting region of the sky where there's a galaxy cluster that lenses stuff behind it. With Hubble, the initial data was all tightly controlled by specific groups who had proprietary access and all that. And here is also the case. There's a lot of that. But in addition, there are these programs that that provide public data that anyone can use very quickly. And they had these, to everyone's surprise that I know, they had these early release images, which weren't even part of that sort of formal program, but just like, let's show off what the telescope can do, at the very first presentation, which is awesome. It's beautiful. And yeah, this is that first image.
Turn the lights down.
Oh, yeah, sorry. Oh, it's very fast. Oh, sorry. Yeah. Oh, yeah, that's much better. Thank you. Yeah, so, okay, we'll do that again then. So this is one image with JWST, and it goes, in these wavelengths, way deeper than Hubble and Spitzer could. Like in the infrareds, where you see all these very distant galaxies, it's like 200-300 times deeper, like right away. Optical wavelengths, the differences are smaller with Hubble because this is optimized for the infrared. But yeah, we see all these galaxies that we couldn't see before, including very distant ones. And so there's a ton of papers that were written on these early data, like right away, because everything was new. This just zooms out. This is a lensing cluster, so you can see these background galaxies being gravitationally amplified by the intervening dark matter. And this is 2 papers that came out, not entirely randomly chosen, but still pretty randomly. There's results right away. Now, whether they stand up to the test of time, we'll see. But basically, there was much more to see than we expected. So there's a lot of galaxies in a very early universe within first few 100 million years after the Big Bang, and bright ones, that were already kind of massive, and some possibly as massive as the Milky Way, that existed already after a few 100 million years. Completely unexpected, that part. So it's exciting, and that's what everybody seems to see. So we'll see whether individual sources hold up, but the overall narrative is there's more stuff that formed early than we expected, and that's great because then there's a lot to see, right? If it was the other way around, if the universe did nothing until the Hubble era, then JWST wouldn't have seen anything. But now we probe further back in time and we see tons of stuff, and these are just follow-up papers from these early papers, with interpretations. And I just picked a few, and this is just the last few months, right? So constraints on dark energy, primordial black holes, what else do we have? Fuzzy dark matter, stress testing lambda CDM that says that these early galaxies could not have formed in standard lambda CDM. You have to do something different. Axion mini clusters. Has JWST already falsified dark matter driven galaxy formation? Any question mark is always no, right? Title that's a question mark, the answer is no. But anyway, interesting that people ask the question, I would say. Anyway, this just shows, like, you build a new facility, people do exciting things with it. There's open data and the possibility to just jump on things, and that will happen. It will happen with Roman. It'll happen with all these facilities that I listed over the next decade, and every couple of years there's going to be something exciting coming. So it's actually really really cool. And then there's these long-term things, with the decadal. Anyway, thanks.
Questions.
Thanks a lot, Peter. So apart from these big things, for example, there are things that are successors of Hubble and successors of LIGO. DESI is the successor of SDSS. Is there any successor in that direction?
Yeah,
because I didn't see like much spectroscopy here, but that's probably because it's small scale, small budget thing relative to these big things. So
it is actually, yeah. So the question is, for those who are not initiated in the acronyms, the Sloan Digital Sky Survey was hugely successful. It imaged the whole sky and then took spectra of tons of things. The spectra really made it unique. But it was done with a 2-meter telescope, so fairly small. No, okay, a little bigger than that, but a fairly small telescope out in New Mexico. And right now, that's being done sort of again, the spectroscopy with a 4-meter class telescope, which is much better, much faster. Also, a modern instrument, DESI, that Yale is actually part of. And the main goal is, again, cosmology. That's often the driver of these projects, but it will produce many, many spectra that are very useful. The question is, what's next there? So one of the priority areas, I won't even try to find it, for those mid-scale initiatives is massive multiplex spectroscopy. That is actually, I think, the only area plus time domain that we listed explicitly. Because that's there's just many people are driving the bus in that specific direction. If you ask, like, here's the photons coming from the sky, what am I doing with them, right? In terms of just collecting them in a broad bucket, it's hard to improve over the Rubin Observatory, because that's a 3-degree field, 6 times the full moon, 8-meter telescope. You're kind of like, okay, that's sort of it. A very high image quality. But if you ask, how many of those objects am I getting a spectrum so that I can measure the distance and the chemical content, et cetera, then there's still huge improvements to be made. you know, because it's only a tiny fraction of the objects. There might be, you know, 1 million objects in a single image of Rubin, but only of like 1,000 will get a spectrum quickly. And so there's a multiple, you know, there's a big factor there in improvement, and people have recognized that. I have to say, sometimes it goes a bit in that direction. Like, oh, there's a niche, you know, we can get more. But no, there's also interesting science to be done with that.
Okay,
But it will be competed. So we weren't in that, you know, relatively low budget. We weren't recommending anything specific, just areas. Yeah. Yeah,
I'll ask my question. So the Decadal and the DOE SNOMAS version of this, you know, on the DOE side, they didn't talk to each other. The timescales were different anyway.
Yeah.
We didn't even start doing SNOMAS until, well, anyway, like a year after. Yeah, also mid-pandemic. But I think I'm noticing more and more sort of co-funded NSF and DOE things. So certainly CMBS4 is an example of that. Rubin also has DOE funding. I think there have been discussions, certainly, you know, to get DOE funding for spectroscopic surveys as well. Is there like a time when we'll actually, when like the DOE and the NSF decadals will start talking to each other, do you think? Or
well, that's even beyond the pay grade of this committee, of course. But we did have the impression, let's put it that way, that DOE was not going to change their priorities based on this survey.
Yeah.
You know, trying to be polite, they couldn't care less. No, I would hope so.
Yeah.
You know, and so I think it's right now it's sort of grassroots almost, where the people writing these reports like us, we know, right? And people doing SNOMAS, they know that there's, and so then it gets written in such a way that they can mesh. But just the way the federal government works, it doesn't seem to be in the same.
Yeah.
So I want to ask about the status of the profession panel and contribution. There has been something like that for at least a couple of decadals, but it seems to me that astronomy is way out in front of other science fields in terms of attention to the sort of functionality, the human capital, as opposed to the metal and money. And I'm wondering what you could say in terms of the impact on the profession that this has had. Obviously, astronomy keeps elevating the importance. And as you say, this is unprecedented in terms of what its recommendations are. But can you say something about how that really will impact the future?
Yeah, you know, it's hard to say because, like you said, there have been similar initiatives before. What we were worried about is that recommendations did not get implemented because it was always an afterthought in these reports. You know, there was not a specific panel. It was sort of not highlighted at a high level. And so we figured, well, that's one thing we can change. I mean, that was really Rob and Fiona who made the call to make it a specific panel alongside the program panels and the science panels. You know, we talked about putting in, you know, hard limits to say, unless you do this, you should not fund, you know, whatever, JWST operations. And that just, it sounded wrong, it sounded off. But I could imagine a future decadal going there, you know, because it's right now, I think what it has done is it has made the conversation in astronomy, you know, very, I think, not prominent maybe, but certainly as a standard feature of like hiring processes and of talking about the future. And I think that is different from other professions. But to be completely honest, we could not find data, hard data that showed like clear, you know, like we did this and that led to that. But not because that didn't happen, but because those data are just very hard to come by. So that's why this is this boring focus on demographics and on data collection and metrics, because it seems that that's the only way to take the next step. But we maybe, we may have gotten that wrong. There was also something about the reports of that panel has its own voice. For instance, recommendations with respect to the summit of Mauna Kea, it had its own, priorities, and we struggled what to do, because on one hand you want to have the reports, our reports and the panel reports to tell a consistent story, but we decided that in this case it was better to let that panel also speak for itself. And so not all the recommendations from the report made it into the final report, like the overarching report, but we didn't edit it either. So, the panel report will still say, that Mauna Kea should probably not be used for astronomy, whereas the main report says, we should, but there should be a input from and sort of a new governance structure, which there is actually now. So it was tough to thread that needle. Yeah.
Okay, I'll keep asking. So as an experimentalist, so in the radio astronomy community, it's felt like there's been some hand-wringing about the fact that radio astronomy at this point tends to be very driven by like engineers and things like that. A lot of the instrumentation gets built by sort of non-lab groups and stuff. One of the ways around that is, more mid-scale and small-scale experiments that are funded enough to pay your graduate students and all that stuff. I have to admit, I maybe didn't read the entire Decadal report. Were there recommendations, specific recommendations about for lack of a better term, sort of beefing up the, instrumentation and sort of mid-scale things, or small pathfinders, et cetera?
Yeah, absolutely. That's on one of the slides I skipped for lack of time. But in the mid-scale, we separated several categories, and one is simply an open call, and another is a call for specific priority areas, which is what's done now mostly. And then the third is for sustaining, existing facilities, like building new instruments for, say, the Gemini telescope, which there's now no clear funding path for. But under the open call, we were very explicit, like that this is where a lot of innovation comes from. This is where the seeds are sown for big things down the road, and even small things that just have a disproportionate impact. So we thought that was very important to have, that intellectual freedom. I think we may have mentioned Chime as an example, but I don't. Yeah. If you want to look it up and it's not there, I feel terrible. I mean, that certainly would be an example in that exact category, and on a much smaller scale, like the Dragonfly telescope, that was in my mind when I sat in that committee. It's like, who could build that? Who's not at Yale and has a bunch of money in their pocket? Nobody. And, that's not good. Yeah. Okay. Yeah. Oh, sorry.
Thanks.
Yeah.